Folks, it's just gone 6 p.m, which means it's time once again for the Oceans Institute livestream. My name is Tina and I am your landlocked host. And today I'm very excited to bring you a special guest from the Australian Institute of Marine Sciences, Marji Poitinen. That's her. She calls herself not a marine biologist. She is actually a spatial ecological data scientist working at AIMS, and she is aiming to understand the disturbances affecting coral reefs and what we can do about it. Today we'll be talking particularly about the interplay between cyclones and corals, two, I guess, quite disparate things and yet connected in an odd and surprising and interesting manner. Marji, welcome to the show.
Marji, thank you so much.
Absolutely a pleasure to have you. For people like me who have no background knowledge at all in either cyclones or corals or how on earth cyclones connect with corals, what is your research all about?
Well, the overriding motivation for understanding how cyclones, or as they're otherwise known, hurricanes or typhoons, impact coral reefs is because there's an urgent need to try and help coral reefs survive. Mm-hmm. And because cyclones are one disturbance that can damage and even kill them, if we understand the time histories of how that has happened in the past and how it varies across the globe, and then we also try to understand how that may change into the future, that can help us prioritize spatially which reefs are the best bang for the buck in terms of conservation. And why should we even care about that is because coral reefs, aside from being amazingly beautiful and having an intrinsic right to exist and worth of their own, actually provide amazing, essential ecosystem services to us as humans on Earth. Mm-hmm. So they protect our shorelines from damage from wave action during storms. And this has been quantified to be worth quite a lot of money. They provide habitat for quite lucrative fisheries that feed millions of people around the world, especially in a lot of the poorer regions in the tropics. They're reservoirs of biodiversity, which is especially important at a time like now where we're facing the coronavirus, because biodiversity is a source for new drug discovery.
See, that's a surprising area for me. I've actually never considered this at all. This is not as perhaps well documented in the news on corals. Corals and drugs, really?
Yeah, so corals have to defend themselves from attack from other organisms, and creatures that live on corals, especially sponges, do this as well. And these active chemicals are often very useful for developing drugs that might be able to work in humans. And then the last part, if any of you have ever been on a tourist trip to a reef, snorkeling or diving or a glass bottom boat, you know what a great experience it was. So tourism is a huge factor around the world. In Australia, it's a big contributor to what we call our blue economy, although not at the moment because of COVID, but under normal circumstances.
When travel returns.
So,
stay tuned.
Yeah.
Coming soon, tourism again.
That's right. I think on the Great Barrier Reef, and I know in Western Australia, tourism operators have been helping scientists with our research when we haven't been allowed to go in the field because they're just sitting there and they can't do anything. So they want to give back to help the coral reef environments that they depend on for their livelihood, and that almost 100% of the time that they dearly love themselves. So coral reefs are really important, yet they're under threat. And I don't know if people that are listening and watching this are aware, but when the ocean gets too hot, more than 1 degree Celsius different than normal, and that lasts for at least a month, that can cause corals to bleach, and I can explain later.
So I'm just showing up an image of a coral that's, so on the left we've got the white coral, and on the right we've got the brown-looking coral. So is that a bleaching event?
That's right. So normally, if you've ever been to a reef, you know that corals have vibrant, beautiful colors, and they come in a wide range of colors. if you see a coral that's bright white, that is not normal for a coral. And that's a sign that it's under some serious stress. And if the water doesn't cool off in time, the coral can starve to death. I guess I could quickly explain how it works. So the reason this happens is that coral reefs are actually a cooperation of millions of tiny little animals that called coral polyps that work together to make the stony structures that we know as a reef. They can feed with their tentacles on tiny organisms, but that takes up a lot of energy, and often more energy than they gain. So they actually have a tiny microscopic plant, which is a photosynthetic algae that lives inside their body, and billions of those live inside their body, and those are called zooxanthellae, and they are what give the corals their color.
That's such a fun word. Zooxanthellae. Yes. That's awesome.
How many words do you know that have a Z and an X in them?
Well, yeah, okay. Xylophone, that's an X.
But does it have a Z?
No. Xylophones.
Oh! So, anyway, these creatures, these zooxanthellae, actually give corals their color. Mm-hmm. Because coral tissue is actually transparent. So if you imagine if I were transparent, I would not be this peachy color. I would be the color of my blood and my bones and whatever that are in me. With corals, they are the color of billions of zooxanthellae inside them.
So, Mari, I found a picture of a bit of transparent coral. It's a close-up of some little tentacle-looking things. Are those the zooxanthellae?
Yes, so the little colored dots inside there are actually the zooxanthellae.
Oh, cool. So, okay, I get it. I think I get it. So the big noodly things are the tentacles.
Those are the tentacles.
Okay, so those are the ones that come out to feed.
Yes, they come out to feed. That's right. And okay. I can give you a link to some great video where you can watch that in time-lapse.
Awesome.
So normally about 90% of the energy that a coral polyp needs comes from the zooxanthellae. Mm-hmm. So let's use the feeding with the tentacles as a backup. But if the water gets too hot for too long, the zooxanthellae, when they do the photosynthesis chemical reaction, it gets supercharged by the extra heat, and free radicals, which are damaging to the coral polyp, are produced. And so that forces the polyp to spit them out. And then once the color is gone, the white color you see is the skeleton that the coral has built for itself, which is white. So that's why they turn white. It doesn't mean they're dead. It means that all they can do to survive now is feed with their tentacles. If that lasts too long and the water doesn't cool off to allow new zooxanthellae to come back in, then they can starve. You'll know they're dead when they get overrun with algae and they change color to those kind of browny, greeny.
Oh, algae. I see. So on the left, you've got the bleached coral, which at that stage, is it fully dead, or do you know if it's dormant or on the way? In that picture, it looks bright white to me, so I think it's still alive, but it's obviously expelled most, if not, its zooxanthellae. Mm-hmm. The other side just happens to be a coral colony that's a brown color. I see, gotcha. Okay. So it doesn't mean that it's dead, and that so. So there is a critical time period for the die-off to occur. Yes, and that varies by species. So some coral species are better at feeding with their tentacles than others. They can last longer while they wait for the coral to cool off. The other thing that can happen, which happened on the Great Barrier Reef in 2017, is if the water temperature gets so hot, there's no time for the corals to spit out their zooxanthellae. They don't starve to death. They just cook in place because it's literally... Oh, no. That has been rare to happen to date. Mm-hmm. I've just thrown up, Mari, a picture of the Great Barrier Reef 2017, but also 2016 and 2020. Oh, excellent. Yep. So the problem with coral bleaching
if it just happens at one or two little colonies and often it's no big deal, they can recover once the water cools off if it does so in time. But sometimes we see these mass coral bleaching events where huge areas of ocean are overheated at once, and then a lot of corals can be affected. And if these happen too closely together so that corals don't have time to recover in between, past 4 years, we've had 3 mass bleaching events on the Great Barrier Reef. So in those pictures, everywhere there's a red dot is where aerial surveys or diver surveys observed severe bleaching somewhere on that reef. And so you can see in 2016, it mainly affected the north. Then 2017, it overlapped a bit, but moved a bit further south. And then a whole nother set of reefs were affected in 2020. So if we have mass coral bleaching happening year after year with no time in between, then that poses a problem for reefs because they'll be affected without the time to recover.
So, Mari, over the course of the last 4 years, these 3 events, do we know what the total extent of affected reef was?
Well, the maps give an indication of that. There's several papers that have been published by Terry Hughes, who carried out these aerial surveys. So we can put links afterwards, maybe, to some of that. I can look those up. And then if you look in those papers, it'll give you the quantitative data.
It looks like a significant,
quite
huge
extensive
amount.
Yeah. But importantly, not every single colony on an affected reef is killed. It's patchy because it depends on what's happening at each individual polyp.
I'm just looking at the chat log. Rob P. Regular Viewer says, will we be voting on Smash or Save today? Team Smash, change my mind. Can we try and change his mind? So Cyclones and smashing, where does this play into it?
Okay, yes, I've gotten distracted by the bigger picture. So the reason we care about cyclones is because of what we've just been talking about. So the smash side we care about because we don't want to try and save reefs that are likely to get smashed. The save side we care about because, as I will show you, the cyclone wave energy can actually cool the sea surface temperature when it's too hot and actually help reefs. And we've shown this with field studies. So I'll talk about smash first, and then I'll talk about save.
Awesome.
So recently, my colleagues and I published a paper where we looked at the wave impacts smashing up corals from severe Cyclone Lua in Western Australia. So I think, are you going to put up that?
I absolutely can. Cyclone Lua.
So normally people will assume, for example, that cyclone waves usually damage coral reefs within about 100 kilometers of the cyclone track. Found with Cyclone Lua, which was
Cyclone Lua, this was the one that was, it looks like the northwest of WA.
Yeah.
Okay. And you were talking about the cyclone track, so that would be the overlapping circles that are growing
inside. Okay, so that's right. So each of those circles represents the position of the cyclone along its track during 1 hour of the cyclone. The colors on the map show you the significant wave height, which is the average wave height of the top 1/3 highest waves. So where it's blue, it's at least 4 meters, which is when you start to get severe damage to reefs being possible. That whole area of color, so that 4 meter wave heights or higher, actually extends up to 1,000 kilometers away from the cyclone's track. That's
wow. And it looks like most of that northwest coast is affected.
Yes, that's right. So if you look closely, you can see 2 little boxes there labeled A and B. And those correspond to reefs where we actually had before and after data. And we could prove with that data that severe impacts did happen at those locations, even though they were 650 and like 780 kilometers away from the cyclone's track. So the point of this is that if we're going to reconstruct how cyclones smash up corals, we need to be careful that we don't oversimplify it. And there are methods for doing this that can make sure we don't underestimate the damage by up to 10 times, which we would have if we assumed it was within 100 kilometers of the track.
So it looks like the damage extends a lot further than you perhaps would think. And so this helps you target which areas are, I guess, more important to focus on?
Yes. Yeah, so I should explain, because people may not realize, it's actually quite tricky to have in situ direct measurements of cyclone waves. We can't just run out on a reef and stick a bunch of wave buoys there because we know a cyclone's coming. So usually we have to use models to reconstruct what the cyclone likely did. Mm-hmm. The map that you're looking at is from a numerical wave model of the cyclone, which is built upon a cyclone wind model based on the cyclone's characteristics. So we can use that then to reconstruct, let's say, over the past 50 years, where the damaging wave energy was from all the cyclones that happened in the world. And then you can work out for each reef location what's the expected time interval or return time between a likely impact. Are they likely to happen every 5 years, every 10 years, every 50 years? And that's how you can feed into then making decisions. So if something's likely to get smashed up every 5 years, it's probably not such a great one to pick for a $1 million project to replant corals on.
Fantastic. Speaking of smashing, should we have a look at some of the damage that can be done? I think you have some images of Scott Reef in particular. So Scott Reef, these were the A and B on this picture?
Yes.
Okay, A and B.
A is Scott Reef. B is the Montara Shoals. So.
Okay, so I've got a picture of Scott Reef right here. It looks like quite a healthy state, normal. I've got a second picture of Scott Reef. Oh. I'm going to hazard a guess and say these are before and after. So before, ladies and gentlemen, beautiful Scott Reef, and after the cyclone. So I'm seeing a little bit of breakage there.
Yes, that's right. So breakage is one of the most common impacts you can have. I know you've got photos there of other types of damage.
I absolutely do. So breakage, that's what we're looking at with all the bits, particularly the sort of pointy
so your branching corals that have the bits sticking out, they're the most fragile corals. And so it's quite easy for wave energy to snap those branches and create broken bits.
But I also have one of Ingrid.
Okay. Yep.
So the Cyclone
and is that
Ingrid.
the big field of coral colonies that have been ripped off and flipped over above the high tide line? Is that the one you've got? I can't see, and it doesn't show on my screen what you've got.
I've got a few of the corals that are dislodged just above the waterline. Yeah,
that's the one. Yep. So in 2005, Cyclone Ingrid affected the Great Barrier Reef. And so it takes a bit more wave energy to cause dislodgement like that. It just dislodged and then stayed in the same place, that would be better. But those actually got thrown up above the high tide line. So that means that they're going to be exposed to the sun when normally they would be underwater. So that's more of a permanent kind of...
So it's a whole coral that's just been completely dumped in a different location.
Yes. On the positive side, from a geomorphological perspective, they'll eventually grind up and become part of the reef. So with coral breakage, it's less of an issue because the broken branches sometimes can reattach to the reef and regrow. Branching corals in general recover much faster. They have a faster growth rate.
I've also got one of some sand that's been moved.
So obviously cyclone waves are very energetic, so they can transport sediments into places where they normally wouldn't be, and they can bury and smother corals, which is what that photo is showing. And I can't remember what else I gave you.
So there's quite a lot of damage that can happen. I want to move back a little bit to your studies on particularly trying to find out priority areas of conservation. I think there's a really nice map that you showed me which summed it all up.
Yes.
This is beautiful.
The
so
figure 4 panel. Yep.
It's a beautiful map with lovely colours. So firstly, what are the colours?
So that one comes from the paper that we recently published. So the different shapes, so the continents obviously are in black. The different colored shapes represent coral reef ecoregions. So geographic regions where corals are known to exist, but they're separated into different pieces because they're ecologically distinct from each other. So the colors that they're shaded in with correspond to how often we expect cyclones that are both really intense or strong and also very large in size. So these are particularly damaging because the high intensity winds spread over a big area and can generate big waves. How often do they come back based on the current climate? So where the colors are red, it's bad news because it can come back like once every 5 years. So that's very frequent because it can take cyclone or corals up to 10 years to recover. And where they're the darkest blue, that means they hardly ever have occurred, if ever, over the known history. So you'll notice straight away that the dark blue is predominant when you're really close to the equator. If you look closely on the map, it's between 8 degrees north and 8 degrees. And that's because cyclones almost never track there.
Okay.
And then you notice that there's a lot of dark red area in the Northwest Pacific. And that is a huge hotspot of cyclone activity, especially big cyclones that are also strong. The biggest cyclone that was ever recorded, which was Typhoon Tip in the 1970s, was actually 2,200 kilometers across. If you can
crazy.
How big that is. It's
how big was the Lua, which was in the Northwest?
So Lua was, they vary in size along their track, but Lua peaked in the low 300s of kilometers.
Oh, wow.
So, it's in radius. So in diameter, double that. So 600.
Okay. Holy moly. So about a third of the size of Tip.
Yeah, Tip isn't normal. Like, that's bigger than normal.
Right.
Where you find the biggest ones does tend to be in the Northwest Pacific.
That's actually quite terrible. So this is obviously terrible, and this is the smash side. So how do cyclones possibly save corals? It sounds like it's all terrible news so far. They can rip them up, they can break them, they can dump sand on them.
Yes, and I apologize.
They come every 3 years.
Who loves corals because I sound so gleeful when I talk about them being smashed up, but I'm not. I
Team
love
smash.
So, as I mentioned, and maybe you can bring up the Kerrigan important figure 1 while I
absolutely
start talking. As a cyclone moves along its track, its high winds generate big waves that can stir up the water column. So if the part of the water column that is already normally mixing with each other, if the water is even deeper than that, so that there is water that never mixes and is therefore really cold, if the cyclone waves reach that far down, they can actually cause that cold water to rise to the surface. And that creates what we call a cool wake, because the cooled water is following the cyclone's track in its wake. And so if this happens at a time when sea surface temperature is rising or is already too hot, that can actually make bleaching stop or stop quicker than it otherwise would, or it can prevent the buildup of thermal stress in the first place so that it never gets hot enough to bleach. So in this picture, we've got 2 hurricane seasons in the Atlantic, 2005 on the top and 2010 on the bottom, and different hurricane tracks. And the little orange blobs are the coral reefs. So you can see in the top there, and the little red boxes are where there were actual study sites on coral reefs measuring coral bleaching and measuring temperature. So in the top one in 2005, it was quite an active hurricane season. A lot of hurricanes went near some of the sites, which were Florida there. And then the other box that's way off by itself to the east, nothing really came, no hurricanes came near there. If you move to the middle column there, the blue colors represent the highest accumulated or total cooling from all those different cyclones. And you can see around those sites where there were lots of cyclones, it's really blue. So there was lots of nice cooling. And in the third panel, which is C over there, that gives you what they call the thermal stress, which is the total amount of extra heat that could be affecting the corals. And the bright pinks are long-lasting thermal stress, and the blue is hardly any total thermal stress. So see that where the cyclone cooling happened, there wasn't much thermal stress, and vice versa. And then and that was shown with the actual field data. So the bleaching, where there were lots of hurricanes, didn't last as long and wasn't as bad as it was where there weren't any. And then 2010 is just another example of how this can happen. So right now in the Atlantic, they're having a bumper season of hurricanes. There's actually 5 named hurricanes at once.
That's quite a lot of action.
But the positive side to that is it's going to be pretty hard for the oceans to get too hot and stay too hot enough to bleach corals right now because the hurricanes are churning it up. So what you want is a hurricane or a cyclone. It doesn't have to be super intense, but it needs to be big and slow moving, and that will maximize the cooling it can do, assuming the right oceanographic conditions, and that without creating the maximum amount of damage.
So you want like a good critical amount of smash. You just want a little bit of churning, some gentle action through the coral reef there.
Yes, just enough to bring the cold water up. But not so much that we smash the crap out of them.
That's awesome. And so, okay, I think that makes sense. But I have a question, I guess, which is about this research in the context of changing climate. Because as the climate changes, I think we will expect to see changes in the patterns of these storm and these cyclones. So how does this all fit in?
So this is where it gets a bit tricky. If you go back to that one we showed before with the return intervals, while you get that up, people often will say, there's going to be more intense cyclones in the future. But actually what the latest consensus of the climate researchers shows is that actually the total numbers of cyclones are likely to stay the same or decline slightly because it's more than just the sea surface temperature. There's about 8 different factors that influence whether a cyclone can actually form. And one of those is the absence of what's called wind shear. So if you've flown on a plane, you may have experienced the negative consequences of wind shear because it can cause severe turbulence. It's just winds that blow straight down and they shred cyclones. So the latest research, one of the factors that inhibits cyclones from forming, even though the water is warmer and could fuel them, is that wind shear is supposed to become more prevalent. But as we've already seen keeps getting dark in here. In the Atlantic, in the Gulf of Mexico with recent hurricanes, once they actually spin up and form, they can very rapidly intensify. So of the cyclones that form, they're more likely to reach those highest intensity categories. So that's kind of bad news for the cool wakes, because we don't need a super strong cyclone. We just need a big, slow-moving one. So anecdotal evidence suggests that cyclones may already be moving more slowly and lasting longer along that trace. But that's yet to be resolved in any kind of physics-based model to explain a mechanism for that. That's just based on observations and only from the Atlantic. In terms of the cyclone sizes, which is really important as well, very minimal research has been done to examine how that's going to change in future climate models. And the most uncertain part is where the actual tracks go. So we know that cyclones tend to transfer energy, heat energy, from the warm oceans of the tropics, and then they always track poleward. Depending on which hemisphere you are in, that will be north or south.
So they'll move towards the poles from the equator.
Yeah.
Okay, so they'll tend to calm down. Okay, that makes sense.
Yeah, and then eventually they encounter enough cold water and unfavorable conditions in the atmosphere that they dissipate. So we know that as sea surface temperatures are getting warmer further away from the tropics, that means they're less likely to die out as quickly as they move poleward. So we can expect them to shift their tracks to persist longer. But in terms of where they form and exactly where they track, and whether the mesoscale meteorology of the other things that are happening are going to change what their typical tracks are, we don't really know that. But it's really important, because if you don't know where it tracks with respect to a reef, how do you know what the patterns are? So I'm working with an awesome PhD student from the UK who may be listening, named Adele.
If you are listening, please let us know in the chat log just to prove that we're live.
So she's been working with outputs from global climate models of projected cyclone tracks and trying to work out the spatial bias in where they are, so we can get a handle on how uncertain we are about this. Because managers of reefs, like at the Great Barrier Reef Marine Park, want to know for specific reefs, what's the cyclone situation going to be in the future?
Absolutely.
So, yeah, a lot of work to do to try and resolve these issues.
Interesting. Just a reminder to the audience, I've got my list of questions right here, and I've got loads more for Mari. But if you have any questions of your own on cyclones, corals, or I guess anything else, now's your opportunity. Make sure you do fill up the chat log with your questions. I want to return to the difference between cyclones. I think you've mentioned a few times there are big and intense cyclones. There are also, I guess, big and slow-moving cyclones. And I just want to clarify a little bit. So what exactly are the parameters that you're looking for when you're talking about these different cyclones?
Yeah, I'm glad you asked that, because in the media, it's very frustrating. When people talk about cyclones, they usually just talk about what category cyclone it is. And if it's a category 5, then it's more damaging to reefs. And if it's a lower category, then it's not. But what reefs care about are big waves coming and smashing them up, right? So wave formation doesn't just depend on the category. So the strength of the cyclone tells you the maximum winds you can get, and those are found at the boundary of that calm bit in the middle that's called the eye, right? Mm-hmm. So how far those strongest winds extend and how quickly they drop off with distance from the eye is controlled by the overall size of the cyclone circulation. Mm-hmm. When you have a really big cyclone, that those high wind and therefore wave conditions take a lot longer to drop off with distance. So you've got a bigger area of ocean that high winds are blowing on, and therefore there's a greater potential for big seas to form.
I'm just showing up an image of Cyclone Waves, which I think shows the comparison between a small and a big cyclone.
Oh, the one that compares Tracy and Tip.
Yes, I think so.
Yeah. So we talked before about how big Typhoon Tip was. You can see it on a map of Australia. And
Typhoon Tip, that's the red circle.
Yes, the giant one.
Okay, and that's not the extent of the waves, that's the cyclone itself.
No, that's just the size of the cyclone. Okay. So, and inside that is actually the size of Cyclone Tracy, which devastated Darwin. Darwin was pretty unlucky because it's one of the smallest cyclones ever recorded, so they really had to get a direct hit. But as you can see on the graph, with a small cyclone, those winds drop off really quick so the ocean doesn't have as much chance to build up big waves. Now, the other thing that goes with that is how quickly the cyclone's moving. So if it's moving really slowly, then the waves that are possible from those wind speeds are maximized, and you're more likely to get the worst possible seas that you can from that intensity. And if it moves really quickly, then you don't. So there's another picture which you can bring up, which is called...
So this is the one which has the
Cyclone Predicted Impacts GBR, which has all the circles.
Yes, absolutely. So this is the circles for the different cyclones. We've got Justin. We've got a few other cyclones up there as well.
So this shows you for the Great Barrier Reef over about 25 years. Going up and down on the graph is the size of the cyclone. Going left to right or horizontally on the graph is the intensity. So as you move up, you're getting bigger, and as you move over to the right, you're getting stronger. I don't know whether you can see it very well, but the strongest one has a tiny little circle.
Yes,
so this
Cyclone Larry, is that Larry?
Yeah, that's Cyclone Larry from 2006 that made our bananas really expensive for a while.
That's right, I remember this.
So Larry was the strongest cyclone ever recorded in the Great Barrier Reef Lagoon. However, it did hardly any damage to reefs, and we did do, Katarina Fabricius from Ames did a field survey of this. And the reason why was it was tiny in size, but it also moved really, really quickly.
Okay.
And reefs only experienced cyclone conditions for like 20 minutes.
So it was fast and it was strong, but very small.
Yeah.
Okay.
So it's the interplay between size and strength and speed, and also, of course, where the cyclone tracks. So if its track takes it near lots of reefs, obviously it has more of a chance to damage more reefs. And you might have heard of Cyclone Debbie from 2017, if you can see it on there. It has a really big circle. It wasn't as strong as Larry, but it moved so slowly. People on Hamilton Island had to shelter in place for almost an entire day, whereas normally it would be like 4 or 5 hours. So it got the maximum it could out of its winds forming into waves. Mm-hmm. And then the other final point is just, if you look at way over to the left-hand side towards the top, that's where you have cyclones that are weak, like category 1 and 2, but really huge in size. And when they also have a big circle, that means they were
so slow,
close to reefs for a long time.
Wow.
So actually, Cyclone Justin in 1997 caused damaging waves over about 2/3 of the Great Barrier Reef, even though it was category 2 at the time. So that's why I'm always saying the intensity of the cyclone is just a part, an important, but only a part of the story. And so if we come up with simple rules of thumb to approximate where we expect damage to happen that only are based on intensity, and distances from the path, we can get it really wrong. And we don't want to do that because we don't want to spend millions of dollars conserving a reef and then find out, oops. And so, yeah.
I was going to say, so we talked a little bit about cyclones in particular, but going back to coral reefs and their value and what threatens them, what are some of the other threats, perhaps less dramatic and visible than cyclones, that are coming up for coral reefs?
Oh, okay. So there's disease. There's predation from crown of thorns starfish, which when they reach plague numbers can eat vast amounts of coral, which has happened periodically on the Great Barrier Reef. There's, poor water quality, which can inhibit their recovery and growth. Then a really insidious thing that not a lot of people talk about, but we've known about for a long time, is called ocean acidification. So as more carbon dioxide is released into the atmosphere from the burning of fossil fuels, this actually changes the chemistry of the ocean. It changes the pH, making the water more acid. And so the entire base of the food chain in the ocean depends on tiny little plankton that float around, and some of them produce skeletons using calcium carbonate, just like coral reef skeletons are produced. And a more acid ocean inhibits this. So for coral reefs, as the ocean becomes more acid, it's harder for them to build back their protective skeletons that keep them safe from being smashed up by waves. And a lot of the ecosystem services that we rely on coral reefs for are undermined by this if they can't maintain the same structural complexity and, vigor of their skeletons that they have now, like especially shoreline protection. So that is a threat that is there in the longer term. One thing that we haven't talked about that would be useful to make sure everyone realizes is how patchy the smash is.
How patchy the smash is.
Yeah, so if you can bring up figure 3 plot in Cyclone Lure Wave Transformation Scott Reef.
Oh, I sure can. That is one of my favorite images from this set.
Yes, Brian Lowe, who is an oceanographer at the University of Western Australia, did the numerical wave modeling runs to produce this. So what it shows you is that coral reefs have a huge impact on wave energy, and this is why they're so useful for shoreline protection. So you can see arrow pointing at North Scott Reef, and then you've got South Scott Reef. That black arrow shows you the direction that waves were approaching Scott Reef during Cyclone Lua. The colors on that map show you the significant wave height. So where it's red on the western side there, it's 10 meters or higher.
Oh, wow.
Where it's blue, it's down to near or at 0. So you can see...
Moly. You can sort of see the shadow of the reef that it's casting.
Exactly. That is what we call it. It's called a wave shadow. So reefs can block or dissipate up to 95% or more of wave energy. Did I say reefs or did I say waves? Reefs. So
you said reefs.
Interact with the complex hard structures of coral reefs, especially, the emergent reef crest and whatever. They dissipate almost all the energy. And in that map, you can see just a little bit of it propagates through the gaps. And the graphs there show you that at the study sites on Scott Reef that James Gilmore from Ames visits every year, we had before and after data of this. And where they were exposed to the most wave energy, like at SL4 and SL3, 6 meter and 4 meter waves, they had 100% relative loss of the branching corals that I said are the most sensitive. but still lost half to a quarter of the more robust brain-like corals that are harder to damage. But then by the time you get to the other side of the reef at SL1 and SS1, where it's blue, hardly anything happened, especially at SS1, where virtually no impact whatsoever. So when a cyclone comes, it never smashes up the entire reef, every single part of it, no matter how big, no matter how slow.
There's always one side that's a little bit worse off than the other side.
It's very patchy, and this is exactly why it's interesting to me, because I have a PhD in geography. So I'm interested in where things are, why they're there and not somewhere else. And this is a very tricky problem to solve from that perspective, because the closer you zoom in on a reef, the more complexity you find in its structure, and therefore the more nuance in how the waves interact with it. And then there's the whole aspect of the structural vulnerability of the corals themselves, which gets more and more complicated the closer you look as well. Depends on their shape, their size, how strongly they are attached to the reef itself, and what that's made of, what other disturbances have happened recently. So it's impossible to build a simple model and get it 100% right. So there's always something more to study or to do to try and improve it. That's why it's interesting. But
you mentioned that you've got a PhD in geography as well.
Well, yes. So that I have one PhD only. It's in geography. Well, yeah, I guess.
So I'm really curious. How did you get into this particular area of work that you're currently in at the moment? What's your career journey?
Okay, so I started off doing my undergrad degree in the United States, and I studied geography and environmental science. And I liked geography because it's a way of looking at the world that you can apply to so many different places, because I'm interested in everything and I didn't want to narrow down to just one tiny little thing. So geography is all about understanding why things are where they are and driving those patterns. So then I did a Master of Environmental Management focusing on coastal environments at Duke University in the United States, which was a 2-year degree. And when I was in the summer, in between the 2 years of the program, we were meant to go somewhere interesting. And everyone was bragging about, I've been in the Peace Corps and I've been in Africa and I've done this. And I guess I'm a little bit competitive. So I tried to think of the most amazing and coolest place in the entire universe I could possibly go to. And I thought back to reading National Geographic magazine, and it was the Great Barrier Reef. So I randomly called up the chairwoman of the Great Barrier Reef Marine Park Authority, and I said, hi, I'm random.
I'd like to come to the reef, please.
I did. I said, we do this thing called an internship where you don't have to pay me and I do stuff for you. And she's like, yeah.
Sounds great. Free labor.
Yep. So I scrabbled together the money somehow through a long and convoluted torture process. And because I was coming from the US, so it was quite expensive. And I went for 3 months and worked there and, did all these dive journeys and whatever. And I met all these people at James Cook University. So then when I went back and finished my degree, and I met my first husband as well.
Oh, just, on the side, as an aside, also met him. But, mostly I studied corals and,
He wasn't my husband yet. So then
Spoilers.
I decided to apply to do a PhD at James Cook University after I was done with my master's. So I moved to Australia, got married, did my PhD. And how I got into cyclone impacts on reefs was Dr. Terry Doan, longtime guru at Ames, was looking for someone to work on that. And it just sounded like such an intriguing and challenging topic that I said, okay, sign me up. Yeah.
Goodness, we're coming close to the end. I just want to finish this fascinating episode today with what I think to be your most important work, which is not the hard science of cyclones and not even conservation, but actually all of the immense effort that you put towards outreach and education and inspiring the next generation. You do so much for engaging young people. It's absolutely amazing. What are you working on at the moment?
Are you going to show that slide of me?
I can do if you want.
Oh,
There's an endless amount of images of you working with children because you're always out in the community. I
started doing outreach with kids because I have 3 kids, and I often go out to sea and I can't talk to them for 3 weeks at a time. And I wanted them to understand that I was doing something really important, and that was the only reason why I was leaving them, and that they should realize that, women and men can contribute to doing something really valuable that gives benefit to all of humanity. And that's what I'm doing. That's why I'm leaving them. So I started just going in each year to each of their classes. Like my sons were in preschool and they were 3. With my daughter when she was 5. And then in 2018, I joined the an international leadership program for women in science called Homeward Bound. And people were doing all these amazing things to try and make an impact and take leadership. And I was so inspired by it. I thought, what can I do right now? And I thought, everyone loves it when I come into the class and talk about what I do. So I love it. Thanks. I just started ramping up and thinking carefully. Like it's confusing to people to understand how coral reefs work. But if you don't understand the basics of how they work, then you don't understand why they bleach. And then you don't understand how to help them. So, I like to go into schools in my spare time. I have an outreach program called What Do Penguins and Coral Reefs Have in Common? And
about as much as cyclones and coral reefs.
Yeah, yes, that's right. So, it's ironic. I hardly ever get to talk about my cyclone work, although I do get kids, when I have enough time for kids year 4 and older, I get them to make coral colonies out of Lego. And so I get them to make a branching coral and a massive coral, like a brain coral. And what they find is that it's almost a perfect model for how corals act in the real ocean. So a branching coral doesn't take as much Lego to get to the same height. So it's fast to build and it's fast. Yes, it's fast to grow, but it's really easy to break. And they find there's a constantly breaking, just like in the real world. And the opposite with the massives. So then I take them through and I say, well, if there's a lot of cyclones and there's not enough time to recover, are we getting with more branching corals or more massive corals? And, bleaching has the same preferential effect to damage branching corals. So if we have bleaching after bleaching after bleaching, what do we end up with? Oh, more massive corals. But then what happens to the structural complexity of the reef and the ability of the reef to provide home for fish and shoreline protection? It's just a way for them to hands-on see what is the impact of what's going down. And I think, kids have a right to know.
Absolutely. And I think it's so inspiring and important, the work that you're doing with them, leading the next generation, because ultimately this is the world that they're inheriting right now. And they're the ones who have the power to work on things, but also have to face the realities to come as well.
Well, what's interesting, one of the things that I do with the kids is I dance around in a coral polyp costume.
Yes, I remember this. It's memorable.
Yes. So the wonderful Libby from Ames in Townsville designed this for me because I needed to take it to Antarctica. So there's a video of me dressed as a coral polyp on the deck of a ship in Antarctica.
Of course there is. I'll drop it in the description box afterwards.
Anyway, so it's a white kids' play tunnel that I wear with tentacles, and then it's covered with Velcro. So the white is the skeleton, and then stuck onto me are all these colored bits, and those are the zooxanthellae. So I can actually get the kids. I tell the kids, my water's too hot, help me. And then they make me bleach. And then I let my water cool off, and then they save me so that they can act out the actual thing. But what I wanted to say was I found earlier this year when I gave a talk at the Oceans Institute, I think I was allowed to talk for 3 minutes or something. So I wore a coral polyp costume, and I got my colleagues to bleach me. And the room full of, adult scientists who are normally quite calm and quiet, they just went berserk. So, and I did a similar thing at the Perth Library with people up to 80 years old. So adults love to engage with science in creative ways just as much as kids do. So I'm trying to do that as well, because I think a lot of people just don't realize how dire the situation for coral reefs. And we didn't end up showing that picture. I don't know if we have time, from the IPCC 1.5 report with the
future stripes.
The different. No, the one with the different colored bars for the different ecosystems. So it's got the Arctic and I can tell you its name.
I think we can. Yes, we can.
It's figure 3.18.
Figure 3.18 coming right up. I think it's a really important figure to end on. I think it really does sum up the problem we're facing.
Yeah. So I can't see whether it's up yet, but I'll just start talking about it. So on the figure, there's up and down. There's a series of bars going across that represent different ecosystems on Earth. And one of those is warm water corals. Another one is Arctic, and the same sort of thing applies to the Antarctic. So the colors on those bars represent impact. That dark purple represents severe, widespread, and potentially irreversible impact. Oops, sorry. I made myself disappear for a second.
You're back. It's okay.
Cool. Okay, so if you go to the coral reef bar, up and down on the vertical axis is the average Earth temperature above what it was prior to the Industrial Revolution. So right now we're in that gray bar around 1 degree hotter on average across Earth than it was before we started burning fossil fuels.
Mm-hmm.
As you move up, you get to 1.5 degrees and then 2 degrees. But right now we're in that gray box. In the coral reef bar, you can see already right now we're almost in the dark purple because of coral bleaching. And if we let the average Earth temperature reach and exceed 1.5 degrees, if you go to this IPCC 1.5 report that this picture comes from, the estimate is that 99% of coral reefs around the world will not exist as we know them now. And that will happen in our lifetimes. I'm 50 years old. That will happen in my lifetime. So it's pretty serious.
I agree.
So, I don't know if I mentioned, but there's a lot of work being done around the world, including at Ames, to try and help coral reefs survive. We have the Reef Restoration and Adaptation Program for the Great Barrier Reef. And this is to try and do all kinds of interventions that might help reefs adapt to the warmer climate, or once the climate is stabilized, help them recover. And that is wonderful, and we absolutely must do it, but we also have to stabilize the climate. So those two things go hand in hand, and that's why it's good to show this graphic, because it's super urgent to do both of those things. And the little way that I can help is that knowing about cyclones cooling, so the cyclone save and the cyclone smash, reconstructing that for the past and the future helps make sure we get the best bang for the buck from the conservation actions that we can take.
What a beautiful thing to end on. I think that's the right sentiment to take, which is to be, I guess, optimistic about the future, but also to be realistic about what needs to happen going forward. It is now 7 o'clock. We've been chatting for an hour. I could go forever if you wanted, but I think our audience might be a little bit hungry. It is dinner time. We might just end on that note, but I feel like there are a lot more questions that the audience will have for you. What would be the best way for them to get in touch with you?
They can send me an email.
I'll just bring up a couple of things. So I've got your Facebook and your Twitter account.
Oh, yes.
I can also put your email in the link below in the description box if you're comfortable with that.
Yeah, so on my Twitter account is a great place to see about the latest papers and academic outputs that I'm doing or that other people are doing that I'm sharing.
Mm-hmm.
On the Facebook page is the great place to see what's happening with the outreach that I'm doing. But if you have a specific question that isn't found there, then of course feel free to email me. And there might be a delay because depending on how busy I am at the time, but I will endeavor to answer you as soon as I can. Fantastic.
And if you enjoyed today's show, please remember also to like, comment, subscribe, and also turn on your announcements, which I think is a different thing altogether. We do a regular live stream coming up. She mentioned the Perth Library. We've got our Perth Library series, which is starting in a fortnight's time, so please do join us for those events. If you're interested in finding out more about coral reefs or other ocean-related matters, check out the rest of the live streams in our playlist. We have now 12 episodes and about to add even more. Please do connect with us at the Oceans Institute to keep up with the rest of our research. It's been lovely. I've been Tina, and this has been Marji. I think it's time for us to say goodbye. Thank you so much, folks, for joining us, and until next time. Bye.
Thanks, everybody.